Hi everybody, it's Keith with Bob CNC. I'm here today with my best friend Bob.
And I am here with my best friend Keith.
And we're here to do some shop talk. Last week we started talking about some
Seems like just a few minutes ago.
Don't confuse me, Bob.
Okay, sorry.
We were talking about some of the parameters you need to be aware of when you're shopping for a CNC.
Yeah.
And we want to help you make the best decision for you.
Absolutely. I mean, there's lots of different CNC machines out there, and they have lots of different parameters. And if we thought if we could make them clear, then you could go out there and look and see what
works right for you.
Yeah.
Yeah. Okay. So last week we talked about the material the machine's made of. We talked about whether you should buy a router or a spindle, which is best. That's kind of a loaded question because it's not a matter of best. It's just what kind of leads into the things you're looking for. Very little on spindle RPMs. We also started talking about the brains of the machine, talked about the processor and the firmware that's used to make it operate.
Yeah, now we're going to have to go back next week and get in a plug. Because we were talking about spindles and you just said something about RPM. Obviously the fancier ones are the more
Well, we could have talked about that. You're the technical guy.
I know. I messed up.
You missed it. Okay, well, go ahead. What do you want to talk about?
Well, on the spindles, we talked about, from the least expensive, the DeWalt 660 is a fixed speed. Now, you can buy a router speed controller, but it's not really designed for constant speed, whereas the DeWalt 611 and the Makita RT0703C, 701C, whatever it is, it has also a RPM controller that tries to keep it at an RPM. And then, of course, your spindles, the air-cooled and the water-cooled, the three-phase, they have different RPMs that it keeps it at a constant RPM. So,
okay.
Now you're going to ask, why is that important?
Well, it is important. Now, with the DeWalt 660 or with any kind of a cutout tool like that, you've got fixed RPMs because it's really not. When the guys built the machine to be used out on the construction field,
they weren't thinking CNC router.
No, they were thinking I'm cutting out drywall, or I'm going to cut through some MDF or whatever to make a hole for them.
Yeah, but what they were also thinking is this tool is going to be used because it's used by contractors, right? Carpenters, and they're abusive, so it's built very well. Which
you
really,
just offended a lot of really nice carpenters that are not abusive.
Well, they are though. Right, they abuse their tools. I mean, if you're using your tools, so anyway, it's built very sturdy. The DeWalt is a good. But
now, when you get into a router, a true router, they are going to be variable speed. Yes, generally speaking, and that is why.
Well, I mean, it really comes down to speeds and feeds, and this is another whole conversation. I think we just released a video a few weeks back.
Right.
But the faster that your bit can spin, and you're taking out a certain amount of chip each side each time it rotates, right? If you have the horsepower and your machine's rigid enough, I mean, all of these play together, then you can actually tweak your RPM or change it so that you can cut specific materials, like aluminum. If you have a really fast RPM, your feed rate may be too fast for your machine, so you want to slow that RPM down. Or like with steel, you couldn't handle the RPMs that you would want to handle with some of the plastics. So yeah, it's an important feature if you're cutting lots of different materials. Wood and plastic, the materials are pretty forgiving, so that you can get by with that. You can also take a shallower depth of pass, right, for each bit to kind of change the parameters. So there's a lot going on there, but an RPM adjustment or being able to change that can have some benefits for you.
It's just a matter. These are things just to be aware of as you're shopping around and somebody's advertising this spindle, or you look at why are we using what we're using.
Right.
Last week we started on something, and then this is where we quit. We were talking about the drive components.
Right.
What moves the Z-axis and the X and Y axis. And in the E3 and E4, we have just a simple belt drive.
Yep.
But with the KL series, it gets seriously upgraded to a Bell Everman design, which is just really cool. So what's the difference between them?
Well, for a smaller machine, a belt drive is pretty decent because you don't have a long length of belt and you don't have a lot of torque. So you're not going to stretch the belt as far. You know, you're not pushing the machine as hard because it's a smaller machine, and it's well, it's not that it's smaller because you can have a heavy-duty footprint or with, you know, a small cutting area, but because it's a lighter duty machine, you can get away with that. As soon as your machine starts getting larger or heavier, then you need to start worrying about belt stretch if you're going to use a belt drive. And Michael Everman invented this design. You glue a belt down, and then you turn the belt over so it interlocks with that belt.
Another belt.
Another belt, yeah. So one's a stationary or a static belt,
right,
and the other one's a dynamic, or the belt that actually moves the gantry back and forth or moves the spindle across the gantry. But the advantage of that is your belt stretch is only from the pulley down to where the belt actually gets interlocked with the other belt. And we can do some special videos on that. I don't want to spend that much time with that, but it's definitely a cool way to do a belt drive with belts and remove virtually all the belt stretch. There's another drive. It's a rack and pinion. Rack and pinions are really an involute gear on a rack, right? And they drive. They do have, you know, I mean, they're pretty nice in the way that they work. They do have some problems in the fact that if you push them too hard one direction, they'll try to pull themselves out of mesh. So what typically people do is spring load them, right, to hold them in there, and that also helps remove some of the backlash. The problem with that is gears are designed to run on a tangent line, and again, I won't go into the details with this.
Thank you.
But if you're pushed past that point, then you get some vibration, some harmonics that your stepper motor has to deal with or your drive system has to do. Now there's one more that we should probably talk about, and I'm going to just call it a screw drive. This can be a simple, just like a simple threaded rod like we use for our Z on our E-Series. It could be an Acme threaded rod, which is a screw that's really set up for driving linear motion, or it's more efficient, maybe I should say. And then of course that you have a ball screw, which is a nut that actually has little balls in it that they rotate on, so you get rid of all the friction, and if you make them precise enough, you can get rid of pretty much all the backlash, right? So those are the different types of drives that you have, and they all have advantages and disadvantages. Like a ball drive is very precise, but it's also very slow. And if you can imagine, if you had a really long machine, like an 8-foot machine, and you had a ball screw that was going on there, it could be precise, it would be slow, but it would also, you couldn't spin the ball screw or the nut or the threaded part very fast, because you would get whip. All of a sudden it would be like a jump rope,
okay,
right? And you can't control that. So there's a length limit. It's slow, but man, is it precise. I mean, you can get really, really precision. My Bridgeport has ball screws on it, right? So,
but the big thing,
yeah,
kind of summarize it, is there's when you understand, when you have in mind what you want to manufacture, the thing you want to create, if you can do it with a belt drive, it's going to be much less expensive, right, than with a highly engineered,
absolutely
stiffer,
and it's going to be faster.
Yeah.
Right. So I mean, well, you know, if you're looking at a ball screw, then I would say that you're probably looking at wanting to cut a lot harder materials. You know, your steels and alloys and stuff. Right. I mean, we're putting a ball screw on the Z for the KL series for precision, really, of the height. It really doesn't have anything to do with, I mean, you don't, it's not as fast, right?
Right.
But that's okay, because it's only 5 inches compared to the 36 or the 48, right? So it's fast enough, right? So ball screws are good. And if you have a smaller machine, I mean, ball screws are great. They're expensive. They're a lot less now since the Chinese have started making them, right? And you know, some of the quality of their ball screws I find have been pretty good, right? So the Acme screw and nut system, actually the KL3 series, if you look at some of a product that we don't sell anymore, I actually made an Acme drive CNC. It would probably go around 120 inches a minute, which is pretty fast for an Acme drive, but you know, it was small again. But that's less expensive, but it's still a more efficient way to drive than a threaded rod.
Then a question that comes up with the KL, when the bit is out of the wood and you're moving place to place, what kind of speed are we talking about?
So for let's just start with let's start with the threaded rod, right? You have to turn that puppy 18, you know, if you like a 5/16 by 18, it means you're turning it 18 times to go an inch, right? And you got to turn it pretty fast to do anything. So like the top speed on the Z drive for the E series is like 20 inches per minute. So let's now compare that to a ball screw, right? We move 4 millimeters, right? So roughly 3/16 of an inch instead of 1/18 of an inch every time you turn it. Then now we can get up to around, I think we're at like 200 inches a minute, but I could be wrong on that. But now we go to a belt drive, and the E3 will easily do 300 inches a minute. And the KL series, well, we're going to try to limit it to 1,000 inches per minute, but I was testing at 1,500 inches per minute. And the reason we're going to limit that on the KL series has nothing to do with the drive's not capable. It has to do with the microprocessor is only so fast to deliver so many pulses to get you that far. So I wanted to make sure that we were within the safe region of that. So yeah, so it's tremendously fast. Right, so my Bridgeport, which has got the ball screws, and it will run at 100 inches per minute max. Of course, it's only 18 inches, you know, is the max travel, so it doesn't take long to get there. But if you can imagine having a 4 foot by 8 foot that only traveled at 100 inches a minute, you'd be like, it'd take you all day to get from one side to the other, right?
Right.
So the larger the machine is, the more zippy that you want it to go from one area. You like that engineering term, zippy?
That was really good.
So I hope that explains that. Does that work?
Yeah, I think we kind of, yeah. Okay. I don't know if you could say too much more.
Okay. I could.
I think you could. The next thing that you'd want to be looking at is the power supplies.
Oh yeah.
And let's see, on the E3 we're looking at a 12 volt and 8 amp a system.
Yeah.
Same for the E4. With the KL you're kicking it up to 48 volt but 7 amps.
Well, two power supplies at 7 amps, so about 15 amps you're running.
Right.
So, you know, really the reason this is, I guess, I don't know if it's important, but you should look at it because you could say that your machine has, you know, so much power, but where are they getting that number from? Well, it's really pretty easy math, right? Power in electrical terms is really how much voltage you have times how many amps you have. Now, I want to go back to the E3 because you said something, people think, oh no, we got more power than we think. So we got 12 volts and 8 amps. However, we set our current on our stepper motors at 1 amp a piece and you got 4. So you're really only driving 4 amps.
Right.
You don't want your power supply to only be capable of delivering exactly what you need. You want some overhead. So we could go with like probably a 6 amp, but we wanted to make sure that we had plenty of overhead so that we don't have power supply issues. So 12 volts. However, somebody asked me this the other day, and this is quite true. If power times volts, or power is amps times volts, it says on my little microcontroller or my shield that I can run 36 volts. That is absolutely true. So if you would take your power supply and chunk it and go buy you a 36 volt power supply, right, at 8 amps, or you know, somewhere close to that, you know, 6 to 8, then you would have more power at your stepper motors, driving them still at the same amount of current. You'd have to adjust your current, but you would notice that your machine was would run a bit smoother, right? So with our KL series is a little bit different, and maybe we'll talk about this too later, but we have servo drives, so they're not even stepper motors, right? And they can pull up to, I think in the manual it said 10 amps. Now we're not doing that, right? But we have supplied them with you know, basically 4 amps at a time. So we need two of the power supplies for each of them, and we're running at 48 volts, which is about the maximum that we can run those. So we want to have the most power available. So yeah, when you're looking at a system, you should definitely look at what kind of power is required. First of all, you want to make sure that you can supply that kind of power. Right, you know, with the VFDs, it's a little bit easier when we talk about spindles because they're three-phase, and most people don't have three-phase. But the VFD turns the 220 and even 110 into three-phase so that you can use it. So yeah, I would definitely take a look and make sure that your system's 110 or 220, and then see what kind of current that everything's pulling, so that you could understand what kind of power your system requires. So it looks like we're out of time again, so maybe we're going to have part 3 on this. What do you think?
Yeah, I think we need a part 3.
Okay.
I mean, there's so much stuff to just kind of bear in mind.
Yeah, and I could just keep talking and talking.
Well, you know, and it's not that it necessarily applies to the buying decision, you know, how you're shopping for something, but it does have to do with the thought process that went through in building the machine.
Well, absolutely. If you're designing a machine for yourself, and maybe this will help the guys that are wanting to do that, you know, you get into CNC machine, you're like, oh, I could do this, and there's no reason why you can't. Right? Yeah, to understand some of these parameters, it definitely will help you design a better machine, or at least know what other people have learned. I mean, and there's lots of good resources out there. One of them is the CNC Zone. I mean, they got lots of people that have made mistakes and put things together and have made improvements that you could learn from. So if you're interested in designing or creating or modifying your own, then yeah, these are some of the things that would be interesting to know.
Well, guys, if you have any questions, of course, you can get a hold of us at
Shop Talk.
Yeah, that's it, at Shop Talk.
What is the address there, Kristen?
Shop Talk at bobcnc.com.
Well, that's good. All right, guys, if you got any questions, go ahead and shoot us an email. We'll see you next time. Part 3.
Next time.